students, how are you? So today we have taken a question where a mass is suspended from a string. Okay, so let us see. Let us say this is the mass. Okay, this is the string, and through this a mass is suspended like this. Okay, and this mass is having certain mass. Okay, let us say m. The question is that a ball suspended by a string swings in a vertical plane. So this is the ball having a mass m, and this swings in a vertical plane, right, like this. Okay, so it is going so that its acceleration in the extreme and lowest positions are equal. Okay, so what is the acceleration at the extreme position and the lowest position? So as we know, this ball will be moving towards here, and let us say this is the extreme position of the ball. Okay, this is the extreme position of the ball. This is the extreme position, right? And this is the lowest, right? And it's given that the acceleration at lowest point and acceleration at extreme point are same, right? Acceleration at lowest point is equal to acceleration at extreme point of this movement, right? This is acceleration, right? Acceleration A. I am writing it over here, right? Now the question is that when the acceleration at both the points are equal, then what will be the deflecting angle of string in the extreme position, right? So definitely the thread will be like this when the ball or the mass reaches the extreme position, right? In this case, the angle of deflection, let us assume this as equal to alpha, right? If this is the angle of deflection, then in the extreme position there is no any centripetal acceleration but only the tangential, right? How? Because if you can just draw the free body diagram at this position, okay, and the component of g will be acting like here, g, right? Now when it will be broken into the tangential and the centripetal, okay, and when you just extend the string length like this, right, then this alpha will become here also, because you see two strings as parallel, right? Now from here, when you break the component, right, you can see this is the position where this is the extreme position, and there will be no centripetal acceleration over here. So the component of acceleration which can be broken towards here is the centripetal one is like this, that is g, that will be g cos alpha. This will be the centripetal, g cos alpha, right? G cos alpha is this is the centripetal, and the tangential one will be like this, right? This will be the only component acting over here, right? So the tangential component is definitely, if this is alpha and if this is the right angle triangle, then the component towards the tangential is definitely g sine alpha, right? G sin alpha is acting at the extreme point. This will be the component acting at the extreme point, right? And this is basically tangential component. Tangential component which is acting at the extreme point. So it's given at the lowest point, it's equal to the extreme point. So when you compare, then we can write g sin alpha into the RHS for the acceleration of extreme point, and at the lowest point it's mva square by r, right? So va square by r is the acceleration, where v is, let us say, the velocity, okay, and r is the length of the string. So definitely, because the ball is swinging into the vertical motion and this will be the radius, okay, so it's equal to v square by l. This is the acceleration at the lowest point, right? Now when you just compare this, you get the relation v square by l equal to g sin alpha, right? So this is the relation which is already given to you into the question, we can say, right? Now the question is that what is the value of alpha, right? What is the deflecting angle of string in the extreme position? What is this? This is the extreme position, extreme. What is this value of alpha? So that need to be calculated, right? Now apply the conservation of energy. By the application of conservation of energy, we can see that half mv square will be the energy at this point, right, kinetic one, and the energy at this point will be the potential, right? And this energy at this point, at the lowest point, when the ball is at the lowest point, will be the energy at, will be equal to the energy at the extreme point, the maximum position. Beyond this, the ball cannot move. From here, it is just taking a u-turn, u-turn, right? So this will not go beyond this. This is the maximum point. This is the max, right? So what we can do, the potential energy at this point, by applying the conservation of energy, apply the conservation of energy, by the application of conservation of energy, energy at this point, which is kinetic, that is equal to half mva square, right? Half mva square. We have considered v as the velocity. I have not explained each and everything into this single page, right, that I am assuming, will be equal to the potential energy at this point. So you can see what is the height of this ball from this point, from the reference, right? This is at a height of, if you just write potential energy, it will be mgh, right? M into g into h. So what is the value of h? Mgh on the top, mgh, so that will be equal to mg l, basically the maximum height, and it is standing over here, right? So the height at this point, if l is there, you can see, if l is there, so l cos theta, this will be equal to, this will be equal to l cos theta, right? So this will be equal to l cos theta, l cos theta, right? So the potential energy at maximum height will be equal to mgl, and at extreme position it will be equal to mg into l cos theta, isn't it? Because l cos theta is the height only over here. So energy at this point equal to mg l cos theta, mgl minus mgl cos theta. So it can, you can directly just deduct m from here, right? And we will be having certain details. Let me show you. Yes. So from here you can see V square by L is here, V square by L, right? So just write V square by L into the LHS, V square by L. Let me write with a different pen so that you can see it very easily. V square by L, and 2 going into the RHS will become 2 into G, right? And since L was taken as common from RHS, so V square by L is there into the LHS. So it becomes 2G and becomes 1 minus this cos theta, isn't it? 1 minus cos theta. And V square by L is nothing but G sin alpha. So just use this relation over here and it will become G sin alpha into the LHS is equal to just write 2G 1 minus cos theta, this one 2G 1 minus cos theta. In fact, all this theta is your alpha, because generally you used to write theta, so that's why just I have written theta over here. So all these are basically alpha, right? 1 minus cos alpha, right? So from here you can see G is cancelled out. This G will be cancelled out, right? If this G will be cancelled out, we have left with sin alpha equal to 2 minus 2 cos alpha, right? So, and when you just square it into both these sides, you will get just sin alpha 2 coming into the LHS minus 2. I'm just solving it, nothing else. Okay, so don't get too much panic. Okay, it's simple step, equal to 2 cos alpha, right? This can be the next step, right? This can be the next step, and from here you can see is equal to 2 cos alpha, and when you just square it, the LHS and RHS, you will get sin square alpha plus 4 minus 2 to 4 sin alpha is equal to 4 cos square alpha, right? Now from here, if this sin cos square alpha can be written into the sin square alpha, by because cos square alpha plus sin square alpha is 1. So cos square alpha can be written as 1 minus sin square alpha, isn't it? So this will give you this minus 4 sin square alpha, and this sin square alpha will become 5 times sin square alpha, right? 5 times sin square alpha, and again here minus 4 sin alpha is already there, minus 4 sin alpha, which is equal to nothing but 0, because this 4 will be cancelling this 4, right? Now this will give you, when sin alpha is taken as common, then 5 sin alpha minus 4 equal to 0. But sin alpha cannot be equal to 0, because the angle of deflection is already there. The angle of deflection is there, right? So sin alpha cannot be equated as 0, right? So this could not be 0, this could not be equal to 0, right? So the next, what we can do, sine alpha equal to 4 by 5. We can write from the second one. From the second factor, sine alpha equal to 4 by 5. This is the value of alpha. The deflection angle of alpha is 4 by, sine alpha is 4 by 5. And what is the value of 4 by 5? We remember 53 degree, right? Sine alpha will become 4 by 5 when alpha is equal to, this gives you the value of alpha as equal to nothing but 53 degree. Why? Because 53 degree is the angle on which sine of alpha is, sine of 53 is 4 by 5, right? So my dear friends, the angle of deflection over here is 53 degree. This is nothing but 53 degree. So the question was that a ball suspended by a string swings in a vertical plane so that its acceleration at the extreme position will be the acceleration equal to into the at the lowest. That we have written, acceleration at lowest equal to acceleration at extreme. So at lowest points it's v square by r. R is nothing but the length of the string, right? So that's why v square by L, acceleration at the lowest, and at the extreme position you can see only the tangential component of the g will be active. So that's why g sine alpha, right? So just when we compare, this will give you relation. Now by application of conservation of energy, kinetic energy at this point will be equal to potential energy at the extreme point. We have just equated it, put up the relation as given, a lowest equal to a extreme, acceleration at lowest equal to acceleration at extreme. That we substituted for v square by L equal to g sine alpha. Over here you can see at this step. Now and solve it, and we get alpha equal to 53 degree. And in this way we have solved this question, my dear friends. Thank you so much for watching. Take care. Bye bye. See you into the next class.